Imagine trying to picture something incredibly tiny and invisible, like the state of a quantum bit. How do we even begin to map out its characteristics and truly understand its behavior? Well, one of the most elegant ways to visualize a single quantum bit, or qubit, is using the Bloch sphere. Within this sphere, the phi angle, often called the azimuthal angle, directly maps to the relative phase between a qubit's computational basis states. This angle specifically tells us how the qubit is oriented around the equator of the sphere, influencing its behavior when measured in certain ways. The Bloch sphere represents a qubit's quantum state as a point on its surface. This point is defined by two angles, theta, the polar angle, and phi, the azimuthal angle. While theta indicates the probabilities of measuring 0 or 1, the phi angle specifically captures the relative phase difference between the 0 and 1 states. This relative phase is not about the likelihood of observing 0 or 1, but rather how these possibilities are interfering with each other. It is a critical component for understanding how quantum algorithms leverage superposition and interference. So, how do we work with this in practice? By applying specific quantum gates, often called phase gates or rotation around the z-axis gates, we can precisely manipulate this phi angle. For example, an RZ gate rotates the qubit state vector around the z-axis of the Bloch sphere, directly changing its azimuthal angle without altering its position on the z-axis. This allows quantum programmers to introduce controlled phase shifts, which are essential building blocks for complex quantum algorithms like the quantum Fourier transform or for creating entangled states. This concept of relative phase, represented by the phi angle, is a uniquely quantum phenomenon with no classical analog. Classical bits are either 0 or 1, with no notion of phase between these states. But for a qubit, this phase difference is an extra degree of freedom, a hidden dimension of information that can be precisely controlled. It is this delicate control over relative phases that enables quantum computers to perform computations that are intractable for even the most powerful classical machines, especially in tasks involving interference. Grasping the significance of the phi angle on the Bloch sphere unlocks a deeper understanding of how qubits store and process information. It highlights that a qubit's power goes beyond simple probabilities, extending into the subtle yet crucial realm of relative phase, giving us a powerful tool to engineer quantum states for computation.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.